An 88 kilogram man stands on a bathroom scale inside an elevator. The elevator will accelerate upward from rest at a rate of 1.2 meters per second squared for t1 seconds. What does the scale read during that time? Okay, let's draw the situation. There's a platform on which we have a scale and then a person. All right, now didn't mean to make it look like a snowman, but okay, so 88 kilograms, we have an acceleration of 1.2. What will the scale read? So the person's weight never changes. Earth's going to pull down on the person all the time, no matter what. So that'll be Fg. And that can be calculated just by mass of the person times G. So 88 kilograms, 9.8 newtons per kilogram makes 862.4 newtons. And so the person's going to feel a normal force in the upward direction. And the normal force at this particular time has to exceed the weight. That's because it has to win. It has to cause a net acceleration upward. And so we don't know what that is yet, and that's what we want to find. But one thing we can do is use the idea that Newton's second law can give us the net force on the person. So what do I mean by the net force? I mean that there's some combination of those two vectors, which is F net. Alright, so let's find F net here using the mass times the acceleration. You would have 88 kilograms times the acceleration that they gave, 1.2 meters per second squared, 105.6 newtons. Now we can do a sum of forces that F net in the y direction is the combination of the normal force in the y direction plus the gravitational force in the y direction. I put the y's on there because now I want to put signs in to keep track of the directions. So we know that the net has to be positive because we're accelerating upward. So put that in. When it comes to the normal force, that's what we're trying to find, so I'll leave it as a variable. But Fg would be considered negative 862 because it's down. Then you can solve that equation for the normal force that's required. Ends up being 968 newtons. That normal force is between the person's feet and the scale. And so the scale is going to read that rather than reading its actual weight. It's going to read what would be considered like an apparent weight. So we got 968 newtons on the scale. The person's supposed to feel heavy at that time because they're being like pushed upward more than normal. Like normally when you're just sitting there on level ground and there's no acceleration, you just feel your own weight. But when you're being pushed upwards, you feel that heaviness. So it'd be like an apparent weight. Anyway, that answer is A. All right, so for B, it says, what if the elevator continues moving upward at constant velocity for a certain time? What does the scale read then? So your person can just be on there. The person has their weight, which is the same as it was before, 862.4 newtons. But that upward force can drop down now. Now that the person is in motion, it can actually just match the weight. And then we'll continue with constant velocity. Whatever velocity we acquired during the acceleration phase, we can now just travel with that constant velocity upward. It's a misconception that people think the force upward has to be greater when you're moving with constant velocity, because like it just seems difficult to raise a person up. But Newton's laws would say that actually if we want constant velocity, we just want balanced forces. So that's going to be the answer to B. 862.4 newtons. And then for C, it says while moving upward, the elevator speed will decrease. Now we have a deceleration of 0.45 meters per second squared. What is the scale reading now? Okay. So when you get to that point, you've still got your same weight as before. Same weight of 862.4. Now we have to drop that upward force down though to a lower level. And that'll cause deceleration. It's not quite like free fall because the upward force doesn't go down to zero. Like if it went to zero, your scale would read zero. But it just goes down. So now if we draw the net force on the person, now there's a downward net force instead of upward. And that is the net. So when you do your equation, you just say F net equals ma. We know what the acceleration needs to be, 0.45. So that's a net force of 39.6 newtons. Now we can write the sum of forces, that the net force in the y direction needs to be the sum of the normal force in the y direction plus the gravitational force in the y direction. We know that this needs to be a negative 39.6 so that they go downward. And we can plug in our weight as negative 862.4. And this will allow us, to solve for f and y. So now it's only 822.8 newtons. So the person reads the scale and they say, oh, okay, I'm lighter now, because there's just not as much force between the scale and themselves at that time. So final answer for C would be 822 newtons.